Welcome to this lecture series in group theory. Last time we looked at the notion of a group isomorphism, or simply an isomorphism. So we defined it in one way, but eventually we figured out that an isomorphism of groups is a map from a group G to a group H, such that first of all it is bijective, and the second is this structure preservation property, which looks like this. So the content of this lecture will revolve around a relaxation of this definition. So here are the problems, and let us get started. So let G and H be groups, and we define a map from G to H as a group homomorphism, or simply a homomorphism, if a certain condition is satisfied, which is the following, which is that phi G1 G2 equals phi G1 phi G2 for all G1 and G2 in the domain group. So we just forget about the bijectivity condition. So this relaxation will be a very fertile concept and will give rise to a lot of interesting notions in group theory, but that will not be apparent in this lecture. It will become apparent in the course of next few lectures. All right, so let's explore this concept a little bit more. We will look at some examples and then some properties of such maps. So first of all, it is clear that every isomorphism is a homomorphism because, of course, all we did was just drop one condition from the quote-unquote definition of an isomorphism. The second example is a nice one. So you have Z, the group Z under addition, and then this one. So the map which takes an integer to its remainder class modulo n, this is a group homomorphism. The reason is very simple, because if you do k1 plus k2, what does it map to? It maps to, by definition, k1 plus k2 bar. But we know that this is equal to k1 bar plus k2 bar. This is how addition behaves in Z mod nz. So that's it. That's why this is a group homomorphism. This one is very similar to the above one. And yeah, so what is the map? It just takes an integer to the kth power of zeta. And what is zeta? Zeta is this particular nth root of unity, 2 pi I by n. So yeah, so this is a group homomorphism simply because if you look at the image of k1 plus k2, we get zeta to the k1 plus k2, which is zeta to the k1 times zeta to the k2. And that's it. That's why this is a group homomorphism. This is the image of k1, that is the image of k2, and that's it. So in some sense, these two examples are exactly the same because of a certain isomorphism between these two groups that we discussed in the previous lecture. So I just wanted to mention that. The third example is a trivial one. So G be any group, H be any other group, then consider this constant map, which takes every element of G to the identity of H. And this is also a group homomorphism. And the reason is very simple, because phi G1, phi G2 is by definition EH, because phi takes the value EH on every input. But EH is EH times EH, and EH is also phi G1, and it is also equal to phi G2. So that's it. That's why this is a group homomorphism. So the constant mapping to the identity, mapping everything to the identity is always a group homomorphism. This third prime one is also a trivial one, but an important one. So here H is a subgroup of G, and this is the inclusion map. So what does this map do? It takes an element little h and maps it to H. Since H is a subset of G, this is a legitimate map. Every element of H is an element of G, and we map it that way. And this is a group homomorphism for trivial reasons. Let me denote this map as, I, not to be confused with the complex number I, just notation I for inclusion. So I of H1, H2 is by definition H1, H2, which again by definition is IH1, IH2, and that's it. And that's a group homomorphism. This one is a scaling map. It takes an integer t and scales it by the integer n. N could be any integer, it doesn't have to be non-zero. So this I leave you to check that this is a group homomorphism exercise. This example is that all linear maps are group homomorphisms. Now that requires some explanation. Suppose V and W are vector spaces over the same field, base field, whatever that base field might be. So a vector space is not a group, right? Vector space is some quadruple. It has an operation of addition and an operation of scaling. But the thing is, if you forget about this scaling operation, the vector space becomes a group. In fact, it is an abelian group under the addition operation. So every linear map now can be thought of as a map between two abelian groups. And since linearity of T in particular demands that the following equation be satisfied, we see that T, a linear map T, is a group homomorphism. Okay. What about this guy? So what is this? This map, let me denote as phi. So what is phi? Phi of T is e to the 2 pi I T. This is the definition, and this is a wraparound map. So maybe a picture will help. This is the unit circle S1. Yeah, I should mention that. What is S1? S1 is the set of those complex numbers which have unit magnitude. So it looks like the unit circle in the complex plane. Okay, and what it is doing is basically, what this map phi is doing is we take this real line, sorry, I meant white. So you kind of, okay, let me draw a squiggly thing. So this real line is kind of getting wrapped around. Maybe this is not a great picture. So let me draw a small circle. This is my S1, and the real line I'm drawing in a curly way. So this is how phi is mapping the real line to the circle. I hope this figure makes sense. And this is a group homomorphism simply because phi of t1 plus t2 is e to the power 2 pi I t1 plus t2. But basic properties of exponential maps show that this is e to the 2 pi I t1 times e to the 2 pi I t2, which is phi t1 times phi t2. And yeah, I should mention, I mean, we discussed this, but S1 is a group under the usual multiplication of complex numbers, and this is the usual multiplication of complex numbers. R is group under usual addition of real numbers. So this equation shows that phi is indeed a group homomorphism. This is another very simple and abstract example. So we have two groups G and H, and what is this map? Let me call this map pi sub G, which takes G comma H to G. So that's the definition of pi sub G. And I want to justify that this is a group homomorphism. So pi sub G of the product of two elements in the product group is, by definition of the product in the product group, or the binary operation in the product group, is this. Now by definition of pi G, this is G1, G2, which is pi G of G1, H1 times pi G of G2, H2. And that's it. That's why this is a group homomorphism. If we look at this equation, we see. Okay. Next one is, this is also very nice. So C star is what? C star is those complex numbers which are non-zero. And this is a group under the usual multiplication of complex numbers. R star is those real numbers which are non-zero. And this is also a group under the usual multiplication of real numbers. And this map is just taking a complex number to its absolute value. And this is a group homomorphism simply because Z1, Z2, the absolute value of the product of two complex numbers is the product of their absolute values, a basic fact familiar from high school. So this justifies that the map shown is a group homomorphism. This one is also in a similar spirit, but still different. So this function is called a signum function. Let me denote it by SGN. Right, so why is this a group homomorphism? Yeah, so what is the group structure? This is a group under the usual multiplication of real numbers. This is also a group under the usual multiplication of real numbers. So this map is a group homomorphism. And let me leave this as an exercise. Trivial. Okay. So this is another important one. So G is just some arbitrary group, and little g is fixed in capital G. So fix such a thing. Then this map, which takes an integer n to the nth power of G, this is a group homomorphism. So if we denote this map by phi, then phi m plus n is by definition G to the power m plus n, which is G to the m times G to the n, which by definition of phi is phi m times phi n, and that's it. So that's why this is a group homomorphism. And this one is a little bit elaborate. Maybe I'll need more space than I've given to myself. Maybe I'll push it a little bit up. So this is what? This is the set of all permutations of the first n integers. In other notation, this is sim of 1 up to n. Okay. And let E1 up to En be the standard basis of Rn. Standard basis of Rn. So with this notation, we need one more notation actually. So define for sigma in Sn, we define T sigma as a map from Rn to Rn as the linear map such that on the basis elements, it behaves like this. So sigma is a permutation of the first n integers, and the map T sigma is defined as the unique linear map, which behaves like this for all I. So for all I in this 1 up to n. A linear map is decided as soon as we decide where the basis elements go. So this is a legitimate definition of a linear map. And now so what is this map P? So the map P is, it just takes sigma to T sigma. So that's what this map is. And this is a group homomorphism because P sigma tau is T sigma tau, and this is T sigma T tau. So all we need to justify is this, but to do that, let me make a box. So T sigma tau of EI is E sigma tau I, which I want to show is equal to T sigma T tau I. But what is T sigma T tau EI? This is by definition T sigma of E tau I, which by definition is E sigma of tau of I, which is E sigma tau I. So maybe I should make a bracket here somewhere. This bracket is supposed to be here, and here the brackets are correct. So let me make another one here. So with this yellow box, it is this equation is justified, and that's why P is a group homomorphism. So this is a way to pass from permutations to linear maps, and this can be sometimes helpful to rather not think of permutations but think of linear maps. Anyway, this is another very nice example. So fix any abelian group and fix some positive integer k. So I should have mentioned that G be an abelian group and k be some, not necessarily positive, just some integer k. Then this map, which takes little g to the k, is a homomorphism. So let me call this phi. And it is important that we are working with abelian groups. The reason is very simple. It's just phi gh by definition is gh to the power k. And now by abelianness, this is equal to that, which is phi g phi h. And that's it. So yeah, this is a nice and important example. And now let us look at some properties of group homomorphisms. So this property we proved for isomorphisms. So yeah, I mean, what is phi? Phi is just some group homomorphism between G and H. This property we saw for isomorphisms, and exactly the same proof goes through for homomorphisms. So this is an exercise. This property we also saw for isomorphisms, and exactly the same proof also goes here. So this is also an exercise. The last one says that if little g is an element of finite order in the group capital G, then the order of the image of little g under phi divides the order of G. The proof is very simple. That's because let order G be equals to whatever n, then phi G to the n equals phi G to the n by using 2. But since n is the order of little g, G to the n is just identity of G. So we have that. And what is the image of identity under any homomorphism? So this is by using 1. We have that. And now this property of orders, we proved that if you have an element of any group and you raise it to, let's say, the nth power and obtain the identity of the group, then that element has finite order, and the order of the element divides the exponent So this we saw earlier. This is just an application of division with the remainder theorem and the definition of order. All right, so this is a nice and important property. Okay. Another two important concepts associated with the notion of a homomorphism are the following, and we'll also see more properties via these concepts. So let phi be a group homomorphism, and we define the image of phi unsurprisingly as exactly the image of phi. Just think of it as a set theoretic object. So this is not a surprise. We also define kernel of phi. So this is read as kernel of phi as those elements in capital G which map to the identity of the group H. And note that the identity of G lies in kernel of phi. So any kernel, so you pick any homomorphism and consider its kernel, then that is non-empty. In particular, the identity of the group will lie in the kernel. Okay? Right, so we have this definition, and here is a simple fact or lemma. Kernel phi and image phi are subgroups. Subgroups of the respective groups, so are subgroups of G and H respectively. So this says that kernel phi is a subgroup of G and image phi is a subgroup of H. So again, this is a very simple thing. So let's first show that kernel phi is a subgroup of G. So how do we do this? So let G1 and G2 be in the kernel. Then phi G1 equals phi G2 equals the identity of H, which implies phi G1 G2, which by the fact that phi is a homomorphism is equal to this, is identity of H, because this is identity of H and that is identity of H. So producting them gives identity of H, which implies G1 G2 also lies in the kernel of H, kernel of phi. And this shows one of the properties that we need to check in order to check that kernel phi is a subgroup. So check as an exercise that if G is in kernel phi, then G inverse is in kernel phi. So once you do this exercise, just combining this and that, we have proven one. And image phi is also pretty simple. It's a subgroup of H. So let me again check the product one. So let H1 and H2 be in image phi. Now since they are in image phi, there exist G1 and G2 such that phi G1 is H1 and phi G2 is H2. Again, we are not trying to say that G1 and G2 are unique, they just exist. So from this point on, I need to add a page. Right, so we have G1 and G2 such that phi G1 is H1 and phi G2 is H2. Then phi G1 G2 is phi G1 phi G2 by the fact that phi is a group homomorphism. So this is H1 H2, which implies H1 H2 is also in the image of phi. And as an exercise, check that if H in image phi, then H inverse in image phi. And with these two things, we see that image phi is also a subgroup of H. I shouldn't say also a subgroup, just a subgroup of H. Okay, another nice thing is the following. Let phi G2H be a group homomorphism. Let K be a subgroup of H. Then phi inverse K, which is a set theoretic concept. What does it mean? It means those elements in G which map to K is a subgroup of G. So what does it say? It says that if you pull back a subgroup under a homomorphism, you get a subgroup. This is like pulling things back. You had a map from G to H, and there is a particular subgroup here. You kind of pull it back. You take its pre-image under phi. So that thing is a subgroup of the domain group. So that's a nice thing. And let's again prove half of it and leave the rest of, leave the second half as an exercise. So let G1 and G2 be in phi inverse K. Then phi G1, phi G2 is in K. By the fact that K is a subgroup, we get this. And by the fact that phi is a homomorphism, we get that, which is of course equivalent to saying that G1, G2 is in phi inverse K. Right? So that's half of the thing. And as an exercise, check that if G is in phi inverse K, then G inverse is in phi inverse K. Right? So again, we never assumed that phi is surjective or injective or any such thing. Don't get confused by this notation phi inverse to mean that phi is invertible. No, phi is just some map, which is a group homomorphism. It might very well be the constant map identity. Okay, so yeah, these are some properties. Maybe I'll do one more property and then we will move to non-examples and finish this. So this is the last thing I want to discuss in this section. So let phi be a group homomorphism. Then phi is injective if and only if kernel phi is the smallest it can be. It has only one element. Kernel phi will always have this element no matter what homomorphism you pick, but we are saying that phi is injective if and only if the kernel is the trivial one. So how much phi collapses things is kind of measured by the kernel. That's roughly what this lemma is about. So first assume that phi is injective. So if phi is injective and G is in the kernel, so what we want to show is that G is actually identity. Then phi E G, okay, so phi G is identity of H. Why? Because G is in the kernel of phi, so this is by definition. But we saw this is also equal to this. So phi G is phi of the identity of G, and by injectivity of phi, this implies G equals identity of the group. So if phi were injective and we pick some arbitrary element in kernel, we saw that it's actually equal to identity. This shows this whole thing implies that. So basically, thus kernel phi is the identity. And the reverse direction is, now suppose if kernel phi is identity and phi G1 equals phi G2, then we want to show that G1 equals G2. Then we have phi G1 phi G2 inverse is the identity of H. All we did was just multiply by this thing on both sides. Now by the property we discussed earlier, this inverse symbol kind of moves inside. We have that, which implies phi G1 G2 inverse is identity of H, which implies G1 G2 inverse in the kernel of phi, which implies G1 G2 inverse is the identity of H. Sorry, identity of G, because we are assuming that the only element in the kernel is the identity of G. So this implies that G1 equals G2. Right? So we started with this assumption, and we want to show that this equation leads to the conclusion that G1 equals G2. That's what injectivity of phi would mean. And all these implications actually show that. And that's why this lemma is proved. Okay. So now let us finish with some non-examples. Consider the map F defined by this formula, which takes an integer and adds 1 to it. Why is this not a group homomorphism? Because the identity of Z is 0, and this map does not map 0 to 0. Identity of Z is 0, right? So any group homomorphism has to map the identity of the domain group to the identity of the target group, but this map F is not doing it. So therefore, this cannot be a group homomorphism. This is not a group homomorphism because, well, let's just compute what is f of m plus n. That is, by definition, the square of it, which is m square plus n square plus 2mn. Now, m square is fm, n square is fn, but there is some extra thing, which is non-zero in general. So what we see is that this equality is not happening, and therefore this is not a group homomorphism. Lastly, this is also not a group homomorphism because, so what is this map? You take any group G and map a given element to its inverse. Maybe one would naturally think that this kind of thing should be a group homomorphism, but it isn't. The reason is f G1 G2 is G1 G2 whole inverse by definition of f, which is G2 inverse G1 inverse. And f G1 times f G2 is G1 inverse G2 inverse. So if G2 inverse G1 inverse equals G1 inverse G2 inverse for all G1 G2, then it implies G1 G2 is G2 G1. But how do I do it quickly? So just take the inverse of both sides, and what we get is G1 G2 equals G2 G1. All I did was operated the inverse on both sides. I mean, there are various ways of seeing this. So we get this for all G1 G2, which implies that the group is abelian. So unless the group is abelian, this is not a group homomorphism. So these are some non-examples, and I think this is enough for one lecture. So as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I will see you next time.